What's up, guys? How are you today? Hope you're having a great day. It's Charles. And today's video is going to be on chemistry structure 2.2, the covalent model. And this video will come after structure 2.1, so I advise you guys to watch that video first. And yeah, let's get right into it. There's a lot of content today, and I'm pretty excited for it. So first of all, what are covalent bonds? So in a lot of scenarios, covalent bonds would be a bond between two nonmetals, but in this scenario, it isn't. So it can be, but and most of the time it is, but you don't define it like that. But what you define it instead is that it's where two atoms they want more electrons to reach a stable electron structure, so they share an electron pair in order to achieve this. And by stable electron structure, we mean by where its valence shell is full. So that's the electron configuration of a noble gas. And the electrostatic attraction between the atoms is going to be known as the covalent bonds. And here's how we're gonna name the covalent bond. So the first element will keep its name, the second element ends with IDE, and we'll have these prefixes to add on to indicate how many of these atoms there are in this molecule. So, but we don't add mono for the first one. So let's like take two examples. So N2O4, so what would it be? It'll be nitrogen oxide, but there's two nitrogen and four oxide, so it'll be dinitrogen tetroxide, okay? And for the next one, hydrogen and iodine, there's one hydrogen and one iodine, so it's gonna be hydrogen monoiodine, okay? And that's how we're gonna be able to name covalent bonds. So make sure you're able to see the electron the molecular formula and get its name, or look at the name and be able to find its molecular formula. Now, the octet rule. So the octet rule is the rule that says there's a tendency for atoms to gain a valence shell of 8 electrons for most of the elements and atoms we'll be working with. However, remember that it's not fixed at 8, okay? There are a lot of exceptions to this, and the ones you need to know is that hydrogen and helium can be stable with 2, beryllium can be stable with 4, and boron can be stable with 6. Beryllium and boron are known as incomplete octets. And for HL students, you need to know that the elements at period 3 and below can have expanded octets, and that's where they can have more than 8 electrons in their valence shell. But we'll talk about that later. And how it really works is, as I mentioned before, covalent bonds are sharing of electrons, right? So some of the electrons they'll be shared, and those are being called the bonding pairs or bonding electrons. And the rest of the non-bonding pairs are known as lone pairs. And in a Lewis structure like this, we'll have only outer electrons. So the magic number is 8 using the octet rule. So in this example, we can see how the chlorine is an element that will want to fulfill its valence shell of 8. Okay, so chlorine adheres to the octet rule, and it's going to be really useful for everybody when we're going to be working on the Lewis structures of covalent molecules. So here are the 5 steps you need to take in order to figure out the correct Lewis structure. So you want to calculate the total valence electrons that all these atoms have, and we're going to calculate all the numbers of electrons for every element to fulfill its octet. It doesn't have to be an octet. I should have worded it better. Calculate the number for all the elements to reach a full valence shell. So how many more they need. And we subtract 1 by number 2 to get the number of bonding electrons. And however many bonding electron there is, 2 bonding electron makes a bonding pair. So we can figure out how many pairs there are in this model. And we'll draw the skeletal structure, and usually with a unique one in the middle, or sometimes the least electronegative one in the middle. And we'll want to complete our octets and make sure that it fits in our previous calculations. So let's do some two examples. Yeah, to get this content in our head. So this one, CCO4. How do we call this? Carbon tetrachloride. Good reminder of the names. So how many valence electrons are there? Carbon has 4 and there's one carbon, so 4 plus, there's 4 chlorine and there's 7 valence for every chlorine, so 4 times 7, so 4 plus 4 times 7 is 32. The number of electrons for all the elements in it to fulfill its octets, both carbon and chloride need 8, so there's 5 elements that need 8, the octet rule, so there's 40. And 40 minus 8 is 8. Okay, so there's 8 bonding electrons, meaning there's going to be 4 pairs in this scenario. And when we draw the skeletal structure, we can find that, oh, it's exactly 4 pairs. So that's all the pairs would need. And then lastly, we need to complete all the octets. So we need to make sure that every element in this scenario has a full valence shell. So and they have 8 electrons alongside it. And do remember that each bond is 2 bonding electrons. Now we can look at the Lewis structure for an ion. So um, OH. Okay. Now I know the word's really small here, but it has a negative there, so it's an ion, an anion. So we're going to calculate the total valence electrons there is. So hydrogen has 1 and oxygen has 6. But because there's a negative, that means, electrons are negative. So a 1 negative would mean there's 1 extra electron. So there's 8 total electrons that we can work with. And the total number of electrons for all elements to fulfill its octet, hydrogen needs 2. Remember, it doesn't adhere to the octet rule. And oxygen needs 8. So 2 plus 8 is 10. And 10 minus 8 is 2. So there's 1 bond. And when we draw the skeletal structure, we find that it's just H and a single bond to O. We complete the octet for oxygen. And lastly, don't forget, because it's an ion, we need to make sure to indicate that we borrowed an extra electron to make it an anion. So yeah, that's how you work with Lewis structures for covalent bonds. Now, single, double, and triple bonds. So in many scenarios, there's going to be single bonds. So that's 2 electrons shared. But when there's 4 electrons shared, it's going to be a double bond. And when there's 6 shared, it's going to be a triple bond. So this is a scenario where there's a triple bond between nitrogen. So the nitrogen as a gas, it can remain stable using triple bonds. And it still adheres to the octet rule. You can see, 6 electrons shared plus a lone pair. A lone pair is 2 electrons. So 8 electrons around nitrogen. And bond order is another concept that we need to know. So the bond order is a number of bonds between 2 atoms, and usually it's just like a single bond, a double bond, or a triple bond. So 1, 2, or 3. But in some scenarios, it can be a fractional number. So I'm going to let you guys look at this one, nitrate. So it's a resonance structure, but we'll talk about that for HO. But you guys can just see the Lewis structure given to you, and there's 1, 2, and 2, a double bond here. So there's 4 bonds in total. But there's only 3 bonding domains, right? There's only 3 connections between N and O's. So the number of bond order it has would be the average. So there will be 4 over 3, or like approximately 1.333, and that's the bond order. And the thing you need to connect with bond order is that the bond length determines the bond strength. Okay, so the strength of a bond impacts a lot of properties of the molecules, and a key thing that impacts bond strength is the length of the bond. So larger bond orders are shorter, so single are really long, doubles are medium long, and triples are shorter. And triple bonds are stronger than single bonds because shorter bonds are stronger, okay? That's all you need to know. And you can see at this helpful diagram down low, the triple bonds are closer to each other, so the bonding strength will be really strong. And that's called bond enthalpy. So that's the amount of energy that needs to break the bond. A higher energy needed to break the bond, meaning that the bond is more strong. Now, coordination bonds. So how can I identify a coordination bond? So coordination bonds are bonded electrons from the same atom. So both of the bonding electrons, they're not shared, okay? I mean, they are shared, but they are both coming from the same element. So one element didn't contribute. And you need to know that once they're formed, that they're just the same thing as a covalent bond. And in this example, we can see that um, of the 6 valence electrons that O has and 4 that C has, for one of the bonds in the triple bonds between them, both electrons are contributed by oxygen because it has more valence electrons. And how you can find coordination bonds in the Lewis structures you draw is you want to count the amount of valence electron each element is contributing and see like if there's a bond that both electron pairs are contributed by the same element. So in this example, it'll be oxygen, but it's gonna be the same property as a covalent bond. So CO, carbon monoxide, it'll have a double bond and a coordination bond. Okay, now moving on to, a lot of people think that this is really tricky, but I think as long as you put some time and work into memorizing the Vesper, it's gonna be so easy on the test. So please, I like beg you, like just remember these. So remember when we know about electrons being negative. So negative doesn't like negative, and it repels each other. So VSEPR stands for valence-shell electron pair repulsion, and it's talking about how the 3D shapes of molecules are affected by electron repulsion. And electron domains is a concept you need to know. So one electron domain can be either a lone pair, a single bond, a double bond, or a triple bond. And no matter if it's a triple bond or a single bond or a lone pair, it counts as one electron domain. And you want to count that, so you want to count the total number of electron domains in a molecule. And you want to remember that lone pairs repel each other more than multiple bonds. So like a triple bond repels itself more than a double bond, which repels more than a single bond. And the reason for that is that so for lone pairs, because they're not shared between electrons, they have a stronger repulsion. And for multiple bonds, there's more electrons there to repel each other. That's a general idea, but it won't really matter. It won't really come up. Just remember that all of these electron domains repel each other, and you need to know all these. And I put some diagrams on the side. So there's two electron domains, and there's two bonding domains. So a bonding domain is like any electron domain that isn't a lone pair. It'll be linear, and the angle will be 180 degrees. For three electron domains, if it has three bonding domains, it's a trigonal planar, and it has 120 degrees as a bond angle. But if it has one lone pair, it'll be bent, where the angle will be approximately 120 degrees. But in reality, it'll be closer to around 117. But just know that. Just write 120 when it's on a test. Though it's not exactly accurate, but still, because you remember lone pairs repel more. For four electron domains, it's a tetrahedral, and if there's one lone pair, it becomes a trigonal pyramidal. Trigonal pyramidal. If it has two lone pairs, it becomes bent. Right. And this all the different bonding domains and the VSEPR structures you need to know if you're SL, but if you're HL, gonna scroll through these and you need to remember each of these. So trigonal, bipyramidal, seesaw, T-shape, that's when there's 5 electron domains. And when there's 6 electron domains, it's an octahedral. It can become a square pyramidal, square planar, T-shape, or linear. Yeah. So just please just memorize those. Like you think like the names are so hard, but like it's literally 3 points if you like spend like 10 minutes on it. So please remember it. Now, bonding polarity. So when we're looking at bonds, when we're looking at covalent bonds, especially, we're thinking about like how they share electrons, right? But what if it's not a fair sharing, right? So we know that both atoms want electrons in order to fulfill their full valence shell. But what if an electron wants it more? What if one of the electrons wanted more? So the polarity, although it isn't ionic, the ionic is basically you're taking an electron. So you're still sharing, but maybe you're sharing unequally, and that's the bonding polarity. So how we can define if it's a non-polar covalent or polar covalent, you need to look at two criteria and this bonding triangle over here. So basically, in most scenarios, the electronegativity difference, which is the quality of different atoms you can find in your data booklet, if it's going to be equal or less than 0.4, it's a non-polar bond. But using this bond triangle, we can know about the second criteria, which is its average electronegativity, and also impact whether it's non-polar or polar. And I'll link to some examples on it. But yeah, so remember 0.4 or under non-polar in most scenarios, and 0.5 and above polar. So the difference in electronegativity. And what this happens is it creates bond dipoles. So basically, because one atom wants the electrons more, so electrons are more closely tied to that one that wants it more. It's closer. It pulls it harder, so it's closer to them. And what this creates is a dipole. So this atom, although it's sharing electrons, there's a slightly positive side where the electrons are far away from, and where the electrons are, that side is slightly has a partial negative charge. And an increased difference in electronegativity leads to an increase in polarity because one pulls it far more stronger than the other, so it's far more polar as a covalent. And how can we identify the molecular polarity? So if we know the polarity of a bond, what is the polarity of the entire molecule? And this will depend on both the bond polarity and molecular geometry. So bond polarity, we just look at that, right? If the bond polarity is nonpolar, then the molecule will be nonpolar. That's what the IV tells us. Not exactly accurate, but if the bond electronegativity difference is less than 0.4, the molecule will be nonpolar. Just say that. And also, you remember the molecular geometry where we have like tetrahedrals or like T-shaped or like trigonal planars. If the dipoles cancel out and there's no net dipole, then the molecule is also nonpolar. And there's three examples here. So for example, carbon, oxygen, and they're a dipole, but the oxygen is facing different directions. So the vectors of the dipole moment is opposite of each other, and that will make it cancel out. So CO2, although the bonds are polar, the molecule is not. And the same thing goes for BF3. You can see it's pulling with equal strength because it's the same bond on all three sides. So that cancels out. And for CCl4, that's the same thing. It's a polar bond, but all the bonds cancel out because it's a tetrahedral. And you will have to say that due to its molecular geometry, the molecular is a nonpolar molecule. All right, covalent network structures. We didn't really go through this in class, but basically you want to know one good example. So allotropes. They're elements that are the same, but they have the different bonding patterns. And a really good example for this will be for carbon. So there's four main ones that are mentioned in the textbook. There's a diamond, there's the graphite, the graphene, and the fluorine. So the fluorine looks like a ball. Graphene is like a single sheet of graphite, and the diamond is like in that shape. And here are some properties that you should know. And also the structure, you need to be able to recognize these structures and know if it's a graphite or graphene. So about its electric conductivity, only graphite and graphene are good at it. About thermal conductivity, only diamond and graphene are good at it. You guys know what a diamond looks like. Graphite is a gray solid. That's a kind of thing you have on pencils. Graphene is a single sheet of graphite, so it's almost transparent. Fluorine is a black powder, and there's some common usages for these different carbon allotropes. Now, this one's going to be everything about intermolecular forces, okay? So 2.2.8 and 2.2.9. So the weakest intermolecular force you have is the London dispersion force, and it's also known as a weak force, because it's weak. What an intermolecular force is think about inter, so international, it's between nations. So intermolecular force will be in between different molecules, okay? So what London dispersion force is that it happens for all the molecules, and basically no matter if it's nonpolar, polar, or like has hydrogen bonds, it will have London dispersion forces, and it's really weak. Again, can't stress that enough because the strength of a bond will really come to play about a lot of properties. And what happens in London dispersion forces is that although like it might be a non-polar bond, but when two of the molecules come close to each other, they can induce into a very temporary dipole, and that would cause like a really weak bond between them because a really really slight positive is slightly attracted to a really really slight negative. So that's an instantaneous dipole, but remember it's really weak and it's a temporary thing. And the next one that's gonna come up is a dipole dipole attraction. So it only works for polar molecules. So what polar molecules have is polar bonds, right? And polar bonds have dipoles. So basically, on dipoles, there's a partial positive charge and there's a partial negative charge. And when two of these polar molecules come into each other, that the partial negative will attract to the partial positive. So these will cause permanent dipoles, and it's significantly stronger than London dispersion forces. So in this example here, we know that in HCl, CO is the partial negative and H is the partial positive. So the partial negative would have an attraction to a slightly positive side, which is the other H. So it's between two molecules. Dipole induced dipole. We didn't go over through this in a class, but I thought it'd be good to add it because it's still in the curriculum. So it's where a polar molecule has attraction to a nonpolar one. And remember when I said about temporary dipole? So what this is, it's basically the same thing, but it's when One of it is a permanent dipole and influences the other one to create an instantaneous or a really temporary one, and that's called dipole induced dipole. So in this case, you can see that HCl has a partial negative, and but two CLs together they're a nonpolar bond. But what happens when they get close is that it kind of influences to have a partial positive side come out, so it's still very weak. Okay, it's a bit weaker than dipole dipole attraction, but it's still stronger than London dispersion forces. And all three of the forces we just went through are known as van der Waals forces. So London dispersion forces, dipole induced dipoles. So these are known as van der Waals forces. And the last one is the strongest. It's the hydrogen bond, and it happens when there's molecules containing the bonds of H and hydrogen, oxygen, or hydrogen fluorine. And the common example here is waters. Okay, so the hydrogen bond of water impacts the property of it a lot. But what happens here is that because oxygen has a stronger electronegativity than hydrogen, so the electrons are closer to oxygen. So the side where the oxygen is has a partial negative charge, and that means the side where the hydrogen is has a partial positive charge, and the partial negative will be oriented to have attraction to the partial negative, right? So in this scenario here, we can see that the oxygen's partial negative is attracted to the partial positives of hydrogen. And hydrogen bonds are the strongest type of intermolecular bonds. So that we've learned so far, and you know, be able to identify it. Make sure that the negative and positive are the ones that are attracting, and make sure that it's between either hydrogen, nitrogen, hydrogen, oxygen, or hydrogen, fluorine. Fluorine. Yeah. Okay, and remember when I said that bond strength is really important? It impacts the properties of covalent molecules. So boiling and melting points. So boiling and melting points is the temperature that changes state of a molecule. And what it basically does is it breaks the bond between molecules. So the stronger the bond is, the harder it is to break. So the higher temperature or energy is needed to break this bond. So a stronger intermolecular force um, will make the molecule have a higher boiling or melting point. At the same time, a larger molecule size will make the London dispersion forces stronger, and a larger molecular surface area will also make the London dispersion forces stronger. And London dispersion forces are a form of intermolecular force. So all three of these criteria will impact boiling and melting points. Because remember, London dispersion forces affect all molecules, dipole dipole affects only polar ones, and hydrogen bonds only influences special polar ones with hydrogen and those three elements I just mentioned. Volatility, so it's a tendency to vaporize. It's kind of similar to boiling and melting points because the less volatile, it means it's less easy to evaporate, so it's harder to break bonds. So stronger intermolecular forces will make a molecule less volatile or less easy to evaporate. About solubility and electrical conductivity, polar molecules are more soluble in polar solvents, and nonpolar is soluble in nonpolar solvents. So on the opposite side, polar is not really soluble in nonpolar solvents, and nonpolar molecules are not as soluble in polar solvents. So, because, yeah, and bigger molecules or giant molecules, they're slightly less soluble. And the ability to conduct electricity. So, how electricity conducts is when there's ions, right? But we know that it's not ionic bonds, it's covalent bonds. So, nonpolar bonds don't conduct electricity. But some special polar molecules, such as HCl, it's a really strong acid. When you add it in water, it conducts electricity well because it was able to ionize in a situation. So, yeah. Okay, now we're talking about intermolecular forces and chromatography. So, chromatography is a technique to separate mixtures, and it's one of my favorite techniques because it's like more special than, like, I don't know, straining it or like picking it out. But there's two types of chromatography mentioned in the textbook: paper chromatography and thin layer chromatography. And basically what it does is, you can look at a diagram below. It's of paper chromatography. So you have a mixture that you want to separate, and you put it in a solvent. And remember when I said polar molecules are more soluble in polar solvents? So sorry, if the solvent is very polar, then the polar molecules will be more soluble in it. So um in a paper, the solvent will slowly rise up, right? For example, water will slowly go up the paper, and water is, as I mentioned, it has hydrogen bonds, so it's a polar one. And a polar molecule like water, okay, the more polar molecules will be more attracted to it. So how it separates is using polarity. So more polar molecules will go further with the solvent, and less polar molecules or non-polar molecules won't go as far with the solvent. So we can calculate the retardation factor. So it's the how far the mixture traveled versus how far the solvent traveled. That's a typo. Yeah, I made these slides. But by looking at the retardation factor, we can distinguish like what part of the mixture is more polar than other, depending on which solvent you're using. On the other hand, if you're using a nonpolar solvent, then nonpolar solvents will run further and have a greater retardation factor than polar substances. All right, SLs, you're done. Great job. But HLs, there's still a lot to cover, and it's like really hard. SLs, you can stay still. Just saying, never hard to, never bad to learn hard stuff because it might come in handy. So resonance structures. So in this scenario, we can see an ozone, right? But there's when you're drawing Lewis structure, you'll find out, oh, wait, there's two different ways that the bonds can go. You can go on the left or you can go on the right. And what's happening here is called delocalization. So when bonding ions are less restricted, it can change the bonding positions. And Lewis structures that has multiple possibility of the bondings when there's delocalization happening is known as resonance structures. And how this is indicated is we have we're gonna put dash lines on top. You see the ozone hybrid. We're gonna put dash line where the possible bonds might have been, and it's called a resonance hybrid. So that's how you would indicate a resonance structure, and you can identify it by in most scenarios when the molecule looks very symmetrical because if it has the same bonds with the same elements, then most likely the bonding position can switch. Or if you can draw multiple Lewis structures and it all works and adheres to the rules, then that also might be a resonance structure. And we're looking at a special example here. It's gonna be called benzene, and benzene's really special and it has a subunit on its own, and it's like really long. So it has a really interesting resonance structure. So as we can see here, benzene is a hexagon with carbon, but it's not just a regular hexagon. As you can see, there's two different orientations where a double bond may occur, right? And how the scientists denoted this was they just put a circle in it because there's like two different denotations of where the double bonds might be there in the hexagon. And they have some very interesting properties due to the delocalized electrons. Remember, it's a resonance structure. It has two potential possibilities and they exist at the same time. And this special benzene shows how, like, in this delocalized system where it's in a hexagon, where, it's double bonds switching each other, how it becomes very stable. And we'll look at some properties here. So we didn't go over this in class, so I figure it probably won't come up like a lot in tests, but I feel like the stuff in the textbook is still good to know. Benzene has special bond length. You would expect like the double bonds to be shorter than single bonds, but it doesn't because it's a resonance structure. It's actually between a double bond and single bond. So like Schrodinger's cat. That's how I like to think of it. Hydrogenation. So basically, like it was put into a reaction, and the result like made it look like it was more stable than scientists expected. And the reason was because delocalization made benzene more stable. Cool. Reactivity. Oh wow, it's not reactive. That means what? It's stable, and that's also due to the delocalized electrons because it doesn't want to disrupt the ring of it. It has a stable structure. As a core resonation, and it prefers substitution reactions. So isomers, if you guys remember, it's in biology we talk about this too. It's like the same same empirical formula and the same like ratio of elements, but it's not the same molecule. And there's not really a lot of isomers. It's pretty special. And the only three is like I think it was bromine with benzene, and it could be put in three different positions. So, it prefers substitution reactions more than like normal reactions, chemical reactions, like when reacting with another substance. That's how I should say it. Sorry. Yeah, but just Keep this on your mind. It might come up. I'm not really sure because Miss Kilson didn't really talk about it, but it's okay. It's okay. It's on a textbook. It's good to know. 2.2.13. Okay, expanded octets. So this goes together with the configurations for 5 electron domains or 6 electron domains. So when an element is from period 3 or below, the central atom can have more than 8 electrons around them. And the two best examples I'm going to talk about is phosphorus and sulfur. So in this scenario, you can see that phosphorus has 5 bonds. And remember, each bond has 2 electrons, right? So 5 bonds, 2 electrons, that's 10 electrons. Wait, that doesn't fit in the octet rule? Yes, it doesn't. So it's called expanded octet. So it fits more than it needs. And if you finish drawing all the octets and realize that, oh, I still have some electrons that should be there but isn't there, just put it on a central atom, especially if it's phosphorus or sulfur. For sulfur, it can go up to 12, There's 6 bonds, 6 times 2 is 12, So sulfur, it's in period 3 or below, so the central, and it's also in the center, so the atom can have more than 8 electrons. So multiple bonds, more than 4, more than 8 electrons. Really cool. Yeah, so make sure you can identify these and like don't get surprised if this happens. And if you're struggling with a Lewis structure, think of the possibility that there might be an expanded octet. 2.2.14, formal charges. So SLs, and they're probably not listening right now, but I'm gonna tell you guys a secret, okay? So they think that as long as the Lewis structure adheres to the rules, it's the best structure, but it's not, okay? And there's one extra nuance to it. It's called the formal charges. So the formal charge of an atom would be how many valence electrons it has, how many unbonded electrons, minus how many unbonded electrons it has, minus how many bonds it has. So there are two goals that you want to achieve for a molecule regarding formal charges. So the first goal is you want the formal charge of every atom to be 0 and the entire molecular formal charge is 0. For the molecular formal charge, you just add up all the atomic formal charges. But if you can't do goal 1, then you go to goal 2, where the overall formal charge you want it to be 0. And if there is going to be a negative formal charge, you want it on the most electronegative element. So we want to identify the preferred Lewis structure if there's multiple that works. And I think this is a really good example. Okay, so for CO2, carbon dioxide, there's two potential things that might work, right? There's one with 2 double bonds or one with 1 triple bond, 1 single bond. And let's calculate. So in diagram A, the one on the very left, the oxygen, okay, how many valence electrons does the oxygen have? 6. How many unbonded electrons does it have? 4. How many bonds does it have? 2. So 6 minus 4 minus 2, that's 0. For the carbon, how many valence electrons does it have? 4. How many bonds does it have? 4. How many lone pairs does it have? 0. So 4 minus 4 is 0. And the same thing goes for the next oxygen. So it's also 0. So diagram A adheres to goal 1. Good. But what happens in diagram B? The oxygen with the triple bond, 6 minus 3 minus 2, that's only 1. And the one with a single bond is going to be 6 minus 1, that's negative 1. And that doesn't adhere to goal 1. So why choose the Lewis structure? You can also call it Lewis formula. Why choose the Lewis structure with not having a good formal charge when you could choose one that's good? So diagram A is going to be the preferred Lewis structure of carbon dioxide. 2.2.15. We're almost at the end here. So hold on. Sigma and pi bonds. So basically it's doing with the interactions with SMP orbitals. So when an s orbital overlaps the s orbital, there's a sigma bond that happens. When an s orbital overlaps head on with a p orbital, it's a sigma bond. When a p orbital heads on a p orbital, it's also a sigma bond. But when there's two p orbitals that's overlapping side by side or parallel to each other, it's gonna be a pi bond. And it doesn't exactly mention why or how this happens because the orbitals are really confusing. But I think the most important thing to know here is to be able to identify how the sigma and pi bonds are in the different bonds that you are looking at. So when there's a single bond, there's gonna be one sigma bond. When there's a double bond, one of the bonds gonna be sigma and one's gonna be pi. And when there's triple bond, one sigma bond and there's gonna be two pi bonds. Okay. Yeah. Last subunit, hybridization. So hybridization happens when an atom's orbital mix together to form new orbitals that can make bonds. that doesn't really make a lot of sense, right? Remember when we talked about, well, I didn't talk about it in the video, but remember when we learned about electrons getting excited, ionization, when they're excited and they jump up orbitals? Well, we were taught that they would always come down, right? But it doesn't have to, which makes it even more confusing. Like, cool. But what happens in this scenario is that the electron jumped up and never come down, so the S and P orbital merged together. So it became a 4sp3 orbital. I'm also not really clear on the exact specifics of this, but I know what you guys need to know. Okay, so in a tetrahedral, the hybridization will be a sp3. Triangular planar, remember the molecular geometry is going to be a sp2 when it's for its hybridization, and for a linear molecular geometry, it's going to be a sp1 hybridized. So I think a really common question, I mean, it might not come up commonly, but I think it'll definitely come up, especially if you're HL. It's gonna show you a molecule, okay, and you want to identify its molecular geometry. You want to identify how many sigma and pi bonds it has. You want to identify, sorry, you want to identify its Lewis structure. You want to identify its formal charges, and you want to identify its hybridization based on its molecular geometry. So, yeah, okay, we're done. Great job, guys. Um, so remember to subscribe for more videos like these. This takes a lot of time, but I really enjoy making this. And good luck on your exams. Over here, who is this? It's Lewis. Is a guy who invented Lewis structures, and he's manifesting every day 7. So good luck on that. Um, if you haven't watched Daniel's video on structure 2.1, check that out. Actually, you should check that out first, but if you haven't, still go and check that out. And yep, I'll see you in the next one. Bye bye.